is Lorenz Halbeisen of ETH Zürich, who will speak on happy families and their relatives.
Thank you. First of all, I would like to thank the organizers for the invitation. It's a great pleasure to give a talk here at this meeting, especially today on Messiah's Day. All the topics I will speak today can be found in Messiah's Happy Families paper. And as Messiah's, I will start with a definition of happy families. But first I would like to say a few words about the name Happy Families. For this I brought here a card game. It's called Happy Families. And if one looks at this, then one sees that there are different families of animals. So there is the frog family with Mr. Frog and Mrs. Frog, Master Frog and Miss Frog. And then there is a fox family and a mouse family and so on. And if we read the description, then it's written, the object of this game is to collect single cards to make up complete families. Now, in happy families in the set theoretical setting, a happy family is a family of sets where you collect singletons from certain sets in order to make a new set which is a member of this happy family. So this is from where the name comes from. So it's very natural to call these combinatorial families happy families. However, there are some people, they call them selective co-ideals, which would probably be more sober, but of course less amusing. So, but now let's start with a proper definition of happy families. We start with a free ultrafilter F. Free ultrafilter. Then we say F plus, which is a co-ideal, is the set of all subsets of omega, such that for all set in F, these sets X are compatible with Z. So they have an infinite intersection.
You really want an ultrafilter?
Yeah, no, not a free filter. Sorry. Yeah. Thank you. And because F is free, this means F contains the Freshe filter. We can also say that F plus consists of all sets, of all the complements of sets Y, such that Y does not belong to F. So this gives us free, from a free filter, the co-ideal. Then we define free families. E, which is a subset of infinite sets of omega, is called a free family. If E equals F plus for some free filter F. And now we are close to the definition of happy families. What we need is also to define for finite subsets of omega S bar. I say S bar is maximum of S plus 1 for non-empty finite subsets of omega. Now, a free family H, free family, and we say H is a happy family if for every subfamily I of H, where I is indexed by finite subsets of omega. So this is a subset of H.
I equals the family.
Yeah, oh, sorry. Yeah, here. For all I, such that the filter generated by the sets in I is contained in H. There exists an X in H such that X is a subset of X empty set, and for all S finite sets of omega, if the maximum of S is in X, then X minus S bar is a subset of XS. So if you have a look at this definition, so H is a free family, and then if you take any subset of it indexed by finite subsets of omega, which are pairwise compatible because the filter generated by I must be a subset of H, and H just contains infinite sets, we find a kind of pseudo intersection. So this X does not intersect all the elements in here, but just the elements such that the maximum of these finite sets belongs to X. So this gives us the notion of a happy family. Now one can ask, are there any examples of happy families? The first example, or the zeroth example, is all the infinite subsets of omega is a happy family. And this is not completely trivial to show this, but the example itself is not very amazing. So one can ask, are there some other happy families which are smaller than all the infinite sets? And a nice example is when we have a mad family, and we build the filter FA generated by the complements of finite unions of A, and put here a plus, so the coideal of it. This is a happy family. Now one can ask, are there even smaller happy families? And for this we have to make the free families smaller, because the free families correspond to F plus, where F is a free filter. It is smallest when F is an ultrafilter. So we can ask, are there some ultrafilters which form a free family? And it turns out that H is a happy ultrafilter abbreviated HUF. If H is happy and an ultrafilter, this is if and only if H is a Ramsey ultrafilter. And Ramsey ultrafilters are called Ramsey because they have a nice property. For every coloring of the two element subsets of omega with two colors, there exists an X in H in this Ramsey filter such that pi restricted to all the two element subsets of X is constant. So this is the reason why happy families, happy ultrafilters are sometimes also called Ramsey ultrafilters. Or to be honest, happy ultrafilters are always called Ramsey ultrafilters. Nobody calls them happy ultrafilters, but today we make an exception. Happy ultrafilters can be characterized by games. We can play the following game with respect to some happy ultrafilter U, or with respect to any family, in fact. The first player plays an element in U. The second player plays an element in X0. In the card game, so one would select one card from this element, and then player 1 plays an element in U, and player 2 plays an element in X1, and so on. And in this game, player 2 wins if this set AN, which he or she has chosen, belongs to the ultrafilter U. Element, sorry. Now U is a happy ultrafilter if and only if player 1 does not have a winning strategy. This characterization of happy ultrafilter we could modify a little bit. We can replace this ultrafilter U we have by some free family E, and then here also replace it by a free family E. Here we get the same. We say if this set belongs to the free family E, and if in this game played with respect to the free family E, player 1 does not have a winning strategy, then we say that E is a Ramsey family. This gives us another kind of free family, and it turns out that Ramsey families are all happy, but in fact not vice versa. So this is Ramsey families are a smaller class of families than happy families, but I will say more about this later. We can also make it a little bit easier for player 2 to win, we say instead of singletons in X, it may play finite subsets. So we have a game with respect to a free family GE star, which is very similar. So x0 in E, then S0, a finite subset of x0, and then x1 in E, S1, and so on. And then we say that, and the player 2 wins again if the union of all this Sn belongs to the family E. Then E, say, is a P family if player 1 does not have a winning strategy. This gives us a larger class of Ramsey families. And we can ask now, are there some P families which are ultrafilters? And it turns out that U is a P point if and only if U is a P family and an ultrafilter. So we can characterize happy ultrafilters with this game, and we can characterize P points with this game G star. So what we have so far are 5 families. We have the happy families, we have the happy ultrafilters, we have Ramsey families, we have P points, and we have P families. And the relation, some of these relations are quite clear. Every happy ultrafilter is a P point. Every Ramsey family is a P family. P points are special P families. Happy ultrafilters are Ramsey families. Then a happy ultrafilter is a happy family, and the Ramsey family, every Ramsey family is also a happy family. An implication which one might expect is that happy families are P families, but this does not hold. And the example is the F, our first example, FA plus is a happy family, but not a P family. So in fact, the other families are, or these families are the relatives of the happy families. Now the second part of this talk.
But is A a math family?
Yeah, here, this is the same example as this example. A is a math family, and then you take exactly what we have here. In the second part of the talk, I will say something about Matthias forcing, and especially properties of Matthias forcing when we restrict Matthias forcing to a happy family. We can restrict Matthias forcing also to a happy ultrafilter or to a Ramsey family, which gives us exactly the same properties, which we will see now. So let's turn to Matthias forcing. As we have seen this morning, the conditions of Matthias forcing are pairs SA, where S is a finite subset of omega, A is an infinite subset of omega, and the maximum of S is smaller than the minimum of A. And then we say that a condition SA is weaker than a condition TB. So we have here the stem S and then the set A. And SA is weaker than TB if T extends the stem S inside the set A, and then the infinite part we get is inside the set A. So this makes S A weaker than TB. And as we heard this morning, we can split Matthias forcing into two parts, or consider it as a two-step iteration. Matthias forcing is equivalent to first force with p omega almost included as a partial order. This adds a happy ultrafilter UG to the ground model without adding new reals, because this forcing notion is sigma closed. And then iterate it with Matthias forcing restricted to this new ultrafilter UG. So we have the conditions SA, same conditions where A belongs to the ultrafilter we have. This forcing notion here is sigma closed, so it does not add new reals. And this forcing notion then becomes sigma centered. And this
what does sigma-centered mean?
Sigma-centered mean if you have if you have any set of pairwise
Union countably many center.
yeah. So this is the reason is that you have just countably many stems, and two conditions with the same stem are compatible because you are here now in a ultrafilter. Good. Now properties. I will put some properties of Matthias forcing restricted to a happy family H. So H could be all the set of all infinite subsets of omega, or a happy ultrafilter, or an arbitrary other happy family. One can show that M H has pure decision. This is also something we heard this morning. Pure decision means for every formula phi and every condition SA, there is stronger condition with the same stem, SA prime, such that SA primed decides phi, which means either SA primed forces phi or SA primed forces not phi. And it has a other useful property, which we also heard this morning. If M is Messiah's generic over V, and M primed is any infinite subset of M, then also M primed is Messiah's generic over V. And here,
Matthias or MH? Yes, works with MH.
MH.
where is MH?
You wrote MH, capital M.
M sub H.
M generic should be MH generic.
Oh, yes. Oh, yes. Yeah, thank you. And here I don't say where I built this subset, this infinite subset of M. So this element we have here has not to be, or must not necessarily be, in the generic extension. For example, when we have a model V and then we extend it with a Messiah's generic M1, and then also M1 is Messiah's over V, and then we extend it again to a model V M1 M2, where M2 is M generic over V M1. Then this M2 is definitely not in VM1, but when we add this M2 to V, then it's still M generic. So M2 is M generic over V. But what we cannot do is we cannot change the order. So if we first add the second Messiah's real to V, and then try to find, or try to compute somehow with M2 and M1 a Messiah's generic which is generic over VM2, then this does not work. So we can, with the information how we build one Messiah's generic into another, we cannot go the other way around. With these two properties, we can show that Messiah's forcing is proper, has the label property, which means that it does not add Cohen reals, but it adds unbounded or dominating reals. So we get from there, we get MH is proper, has the label property. One can also show that it adds dominating reals. Dominating. Oh, unbounded. Yeah. So yeah, just when you add the ultrafilter. Yeah. Unbounded reals and so on. The third topic of this talk, which can also be found in Messiah's paper, is the Ramsey property. So again, we have seen the Ramsey property on Tuesday in the Briscoe's talk. A set A of infinite subsets of omega has the Ramsey property if there exists an H, an infinite subset of omega, such that all the infinite subsets of H belongs to A, or none of them. And it is called the Ramsey property because with a set A we can easily define a coloring of the infinite subsets of omega, saying that an infinite subset has color 1 if it belongs to A and 0 otherwise. And so comes the notation, which we also have seen this morning, which means that all sets have the Ramsey property. We also have heard that Messiah's constructed a model assuming an inaccessible in which all sets have the Ramsey property, and also one in which all the projective sets have the Ramsey property. And one can ask whether one can take this Messiah's inaccessible away. And to solve the problem, one could try to copy or to transform one of Schellach's proof. Schellach proved that it's possible for the bare property, but not possible for Lebesgue measurable. If one tries to copy this with the bare property, one could say the Ramsey property is the same as having the bare property, but with respect to another topology, the Ellentag topology, which is much finer. So it seems that one can just translate the proof. However, the bare property is related to Cohen forcing, which is CCC, and the Ramsey property is related to Messiah's forcing, which is far away from being CCC. So there's no way to just copy the proof. So then one can try the other proof of Schellach to show that if all sigma 1 3 sets have the Ramsey property, then this implies an inaccessible. So this result we have for Lebesgue measurable. If one has a look at Schellach's proof, then there appears a Raisonnier filter, and this Raisonnier filter is defined by measures, but we don't have measures with respect to the Ramsey property. A set has it or has it not. It doesn't have it for 1/2 or something like this. So one cannot define, there is no natural measure for this Ramsey property. Another way, something else one can try, which also does not work, but anyway, is to find another property which is related to the Ramsey property, but somehow easier to handle. And Yuda introduced the notion of absoluteness. We say that V, a model of ZFC, is sigma 1 n Matthias absolute if for every sigma 1 n sentence phi, we have V models phi if and only if the extension, so by adding an arbitrary Matthias real to V, if V of m satisfies phi.
Now, on the right hand side, do you have for all m or the
Yeah, for all m. For any
yeah.
for all m Matthias generic. So this means a model is sigma 1 n Matthias absolute if it does not change the sigma 1 n theory by adding a Matthias real. And then there is a nice result which tells us that sigma 1 2 Matthias absoluteness is equivalent, no, sigma 1 3, because sigma 1 2 formulas are anyway absolute by Schoenfield's absoluteness. So sigma 1 3 Matthias absoluteness is equivalent to sigma 1 2 Ramsey. In the proof, one first just gets from sigma 1 through 3 Matthias absoluteness delta 1 2 Ramsey, but there is a result of Yuda and Schellach which tells us that delta 1 2 Ramsey is equivalent to sigma 1 2 Ramsey. Now one can try to push it a little bit further.
Who proved this theorem?
This one, me. No. So sigma 1 4 Matthias absoluteness, one can show that this implies delta 1 3 Ramsey, but not vice versa. And one can also show that it even implies sigma 1 3 Ramsey. And if the same happens as with Lebesgue measurable, one would expect that sigma 1 3 Ramsey implies an inaccessible, so which means that omega 1 is inaccessible in L. Unfortunately, Brendle showed that sigma 1 4 Matthias absoluteness implies that omega 1 in V is inaccessible in L. So we don't get the inaccessible from sigma 1 3 Ramsey, but from sigma 1 4 Matthias absoluteness. But there is still some hope that one can show the other direction, but the hope is small because sigma 1 4 is far away from Schoenfield's absoluteness, and you don't see a way how we can get the other implication. Now let's turn to the last part of the talk. This will be about the existence of happy ultrafilters. We know that if you have the continuum hypothesis, for example, then there are 2 to the continuum pairwise non-isomorphic Ramsey ultrafilters. So there are models with a lot of happy ultrafilters. To build a model in which there are no happy ultrafilters, it's enough to take a omega 2 iteration with countable support of Matthias forcing starting in a model, say L. This gives us a model in which there are no happy ultrafilters. In this model, we also have that H equals omega 2 and P equals omega 1, because Matthias forcing increases the cardinal characteristic H. And as a nice fact, I would like to mention that in a omega 2 plus 1/2 iteration, with countable support of Matthias forcing, there are again happy ultrafilters. And what do I mean by this 1/2? So this is just the first part of Matthias forcing. Since this gives us a new happy ultrafilter. And now we know that this forcing collapses the continuum to H, and because in this iteration we have H at omega 2, so nothing happened with H, and we have again 1. So we really have to stop after this omega 2 and not put 1/2 more. Now, at the end, as a kind of present to Adrian, I will sketch the construction of Schellach to construct a model in which there are 71 happy ultrafilters. Adrian asked me to construct 71 and not just 70. Yeah. So I leave it to
71.5.
this I cannot do. So.
That's one moderate.
Huh?
One moderately happy.
One moderate. Yeah, there is a notion of moderately happy families, in fact, and which is closely related to P families and to P points. A moderately happy family, which is an ultrafilter, is always a P point, for example. So, how the construction works. We start in a model with GCH. So this means that we have a lot of happy ultrafilters, and we pick 71 out of this two-to continuum happy ultrafilter, say U0, U1 up to U70. Above these Ramsey ultrafilters we have P points, and beside these 71 happy ultrafilters we have some others. Say U primed, and above them again P points. Now, Scheller constructed or defined or found a forcing notion which he calls SPV, where V is a P point, some arbitrary P point. And he shows that this forcing notion has certain properties. It is proper, omega bounding, and has the P property, which is this property. So in Scheller's book there are about 5 PP properties, but they are different ones, but they are always called PP property. And they are weaker than Lever property, but you can catch some branches in the tree. So this is a tree forcing. I will explain it later, such that you get control over the new generic, also over the new reals which are added. And because it's proper, we can iterate it, and this PP property is preserved under iterations. And now the two main results he proved. This is the following: if so B is a P point, and we can show that if we force with this P point, then this P point cannot be extended to a P point. Not even later in the iteration. And for this, to show this, he uses the PP property. So if you have here some P point V, and we force with SPV, then this P point is destroyed, cannot be extended to a P point anymore. And so also the ultrafilter, the happy ultrafilter, which is below. So this this forcing kills. You can kill a certain P point, and with this P point also the happy ultrafilters which are below. And then another property he uses is the following: if U is a happy ultrafilter, V a P point, and in the forcing extension SPV, we can not U does not generate an ultrafilter, So if you have this situation, then this happy ultrafilter U is below V in the Rudin-Kiesler ordering. Or in other words, if U is not below V in the Rudin-Kiesler ordering, then this implies that U generates an ultrafilter. And because our forcing notion is omega-omega bounding, one can show that if a happy ultrafilter generates an ultrafilter, then this ultrafilter is a Ramsey ultrafilter. So this implies that U generates a happy ultrafilter. This means that all the happy ultrafilters which are not below this particular P point, they are preserved. And now the construction is as follows. By a bookkeeping argument, we make sure that all P points which are not above one of these 71 gets killed by this forcing. And at the end, we just have these 71 happy ultrafilters. And we also have that all the P points which are remaining are above one of these 71 happy ultrafilters.
And why do they stay which one?
This one, because they are Q points and the forcing notion is omega-omega bounding. So you cannot, they cannot become isomorphic. So this is what we have here. So we surely know that they generate ultrafilters. So they generate definitely happy ultrafilters. And so by an argument, so you have to need this omega-omega bounding to show that you, otherwise you can do it in the ground model. Tomorrow, I think we will hear more about this forcing notion in Martin's talk. So I think this is a good point to stop. I thank you for your attention.
Is Shayla's paper accessible in human readable form?
What should I say? Probably not yet. So, yeah, almost. Yeah.
This old paper is
So this is in the book. Or not? Yeah. The construction is in the book, chapter 6, part 5. But I will definitely write it again. Yes.
There were some small gaps in
Yeah,
that.
there are some-
discovered, and I
Yeah.
also couldn't fix them. So we asked Safron if he couldn't fix them either.
Yeah, but they are now all fixed and yeah. So it was correct, but it was hard to understand, except at least for me. But now yeah.
Any more questions? Right, if not, let's thank Lorenz. And we resume at 1:30.